Hi, everyone. Welcome to the fourth seminar. Thanks for joining us today. I'm Kara Brugman, research scientist and outreach coordinator for FORCE.
And I'm GUSEV Tsuno, research scientist, FORCE research scientist as well.
And today we have a seminar for you from Dr. Zhang from Texas A&M University. This will be the last seminar of the semester. And I want to remind you all that this meeting is being recorded and will be available on YouTube. You can also follow us on Twitter, LinkedIn, Instagram, and join our mailing list at force.asu.edu/newsletter. All of our past event recordings are up on our website under events, past event recordings. You can see we also have our town hall from earlier this year up there. And we're also going to be at AGU, GUSEV and Logan, and a lot of Dan Shim's lab, who some of them are here on this call too, are going to be at AGU. And so there'll be some kind of like dinner meetup, and we'll have more details about that in the next month. Also, winter workshop signups. I assure you this is coming. Hopefully it'll be open today. If not today, then next week at the latest. We'll be able to give you that link and information about hotels. And before we go into the seminar, I wanted to show you a picture of what's going on with Ichiban and the press lab right now. We've finished the catwalk that goes around Ichiban. So you can see this is the upper part of the press sticking out. At the left, you can see on the floor, there's a hatch here. So our bridge crane, which is that orange thing at the top, that'll be used to move the guide block over to the hatch, lower it through if we ever need to replace something or get it serviced. And then you can see on the right side, just in the corner there, there's a thing that looks kind of like, I don't know, like a little cage. That's actually surrounding the top of our plunger pumps. So that's where you'll come up onto the platform, up the stairs. There'll be Ichiban in front of you, and then you'll have the control box and everything that you need to prep before you put the experiment in the machine right there. It's really exciting. So the roll-up door in front of Ichiban will be put up, I think this week. It might have already gone up. I think I saw them delivering the forklift yesterday. And then we have the IHPV being delivered in maybe December or January. And of course, Jasmine, our dia made by Vogenrider, will be delivered in the summer. All right, so without further ado, I'll turn it over to GUSEV to introduce Dr. Zhang.
So Professor Zhang is an associate professor at the Texas A&M University, and she obtained a PhD in University of Illinois at Urbana-Champaign. Then she moved to University of New Mexico as an assistant professor, and now she's in College Station, Texas. So her research focuses on exploring the structure, composition, and dynamics of the Earth and the rocky planets using laser spectroscopy, synchrotron X-rays, electron microscopy, and diamond anvil cell and large volume press. So Jing, thank you for giving the talk, and the time is all yours.
Hello, everyone. Thanks a lot for inviting me to give this talk at the fourth seminar series. It was really nice to meet everyone online, especially after almost a year of being in the lab every day to set up the lab and stuff like that. It's nice to actually talk with people about science. So today, as you can see from these pictures, I'm going to talk about the Mars, which is the red planet in our solar system. This work is primarily completed by my student Wenyi Zhou with the help from another student, Ming, and it's actually part of her PhD thesis. And of course, I need to thank my collaborators like Carl, Chip, Peter, and Josh. They're super helpful in further shaping this idea that I'm going to talk about today, which is shown in the title that you can see. The lack of plate tectonics on Mars is probably linked to the buoyant nature of Martian eclogite. So, by the way, anyway, I mean, feel free to interrupt me if you have any questions, okay? All right, let's start. So we know that the Earth and Mars are sister planets. Although the Earth is a much larger planet, they're both terrestrial rocky planets made of rocks plus iron nickel alloy. Whether the Mars has a solid inner core still remains unknown, but now with the InSight mission, we already have a relatively good idea about the core mantle boundary depth or pressure, basically, inside the Mars, which is already a big step forward. compared with the Earth, with the Mars, the Earth is extremely active. The violent volcano eruptions, active faulting, large earthquakes, everything like these are telling us that the Earth is not a peaceful planet. The Mars, on the other hand, is a lot quieter, although not silent. Various rovers landed on Mars have been and will continue bringing us more information about its surface geology. And the InSight mission has detected a lot of small seismic events. This video over here shows the first seismic event that InSight seismometer actually detected. I don't think it will play here, but it's okay. It doesn't matter as much. So with these small seismic events, including some of the impact events, scientists now can have a much better understanding on the internal structures of Mars. In any way, the Mars lacks ongoing tectonic activities such as volcanism, large earthquakes with magnitude more than 4, and mountain building processes. So why the Mars and the Earth are so different? I mean, even sisters can have different personalities. The Earth has a relatively active personality and has plate tectonics working, whereas the Mars has a quiet personality and is dominated by the stagnant lid convection. The chemical mixing and mantle convection is very efficient in the Earth's interior, which is not the case inside the Mars. For the superactive Earth, eclogite, which is the high-pressure metamorphism product of Mid-Ocean Ridge Basalt, is a very, very important rock. Let's look at this classic Geology 101 plate tectonics figure. The Earth's mantle is made of this olivine pyroxene rich rock called a pyrrolite. As the slab subducted down into the Earth, the oceanic crust would turn into or transform into this extremely nice green red rock called eclogite over here. This is one of the major geochemical heterogeneities in the Earth, and it is often thought to be linked to the enriched mantle geochemical reservoirs. The most important geophysical property of eclogite is that it is super dense. Compared with the Earth's ambient mantle, which is made of, again, pyrrolite, it's about 5 to 10% denser, and that density contrast preserves down to the bottom of the transition zone, which is about 660 kilometers deep in the Earth's interior. This is believed to be one of the most important driving forces for slab subduction in the Earth. But why eclogite is so dense? Eclogite is made of 2 major minerals with 1 minor mineral. The 2 major minerals are garnet and clinopyroxene, and the minor mineral is silica polymorphs. Eclogite is stable up to 500 kilometers deep before they transform into garnetite. Depending on the depths we're looking at, the silica polymorphs can be quartz, calcite, or stishovite. The clinopyroxene in the eclogite transformed from warp is actually amphasite, which is basically an iron-bearing diopside-rich pyroxene with small amount of a jadeite component. It has a chemical formula like this. You can see that it could contain only a very small amount of aluminum, depend on how much sodium we have in the eclogite. Garnet is a mineral that makes eclogite super dense because it is very, very compact and it has very high density. Just from the chemical formula that you can see, it is a predominant mineral for aluminum, hosted mineral for aluminum, basically in eclogite. So as you can see from here, the more aluminum you have in the basalt, that means more garnet that will form in the eclogite, and then the resulting in a very high density from the transformed eclogite. So again, more aluminum, more garnet, denser eclogite. This is the key for today's talk. Okay, this figure shows different mineral proportions in the eclogite metamorphosed from warp and how that changes with depths. You may notice that the clinopyroxene proportion gradually decreases with depths, and that is because the pyroxene gradually dissolves into the garnet structure at depths. As a result, the garnet and clinopyroxene compositions will change with depths as well. For example, the garnet changed from a pyrogrossular dominant chemistry into a majorite grossular dominant chemistry. So you see a lot more magnesium silicon, in the majoritic garnet. At 250 kilometers over here, you can see roughly about 40% of garnet in the eclogite. This figure shows the density change as a function of depth for both MORB and ambient mantle. Black line shows the calculated density of the ambient mantle model, pyrrolite. And the gray dashed lines are the seismic models, PREM and AK135. Pink and blue lines are the densities of MORB along 1000 Kelvin and 1600 Kelvin mantle adiabat. You can see clearly, again, MORB after it transformed into eclogite remains denser than the ambient mantle down to the transition zone depths, although the density contrast drops at 410 kilometer depths because of the olivine to quartzite transition in the ambient mantle pyrrolite. So basically, slab subduction and the mantle convection inside the Earth is primarily driven by two things. Number one is, of course, the lower temperature of the slab. Basically, the colder, the denser. We can call it a negative thermal buoyancy. And the other one is the one we just talked in the previous slides. Denser eclogite compared with ambient mantle. So we can call it as sort of like a negative chemical buoyancy. For the Earth, subduction is not that difficult, at least in the top 660 kilometers. Mars, again, as the Earth's sister planet, it lacks subduction-driven plate tectonics or mantle convection like the Earth. Why? People have actually proposed quite a few hypotheses before to explain this phenomenon. For example, Slip proposed that the spreading of seafloor caused by the cooling mantle is the reason why the subduction fails on Mars. However, as we know, the ridge push force is not the major driver for subduction. Its magnitude is at least a node weaker to power plate motions. He also suggested that the Martian crust produced by the fast-spreading seafloor can be very, very young. Therefore, it's too hot to sink into the mantle. Lenderk et al. Suggested that the warming Martian mantle resulted in lower mantle viscosity. Therefore, the lithosphere is very difficult to be broken by the mantle convection. So plate is difficult to form from the beginning. Azuma and Katayama proposed that the lack of plate tectonics is due to the water loss at the Martian surface. Basically, with less water in the lithosphere, it could be too strong to be broken into different plates. So formation of the plate at the beginning will be very difficult. All the above explanations are very interesting and might explain the lack of tectonics on Mars to certain degrees. However, all of them assumed some anomalous mechanical thermal properties of Mars, such as anomalously cold mantle, hot crust, ultra-low viscosity mantle, extraordinarily strong like lithosphere. So the question here is, like, could we come up with some other alternative explanations that does not require assuming any anomalous properties of Mars? Well, that's exactly what we did here. Let's look at the compositional difference between the silicate Mars and silicate Earth. Assuming a pyrolytic Earth, the magnesium to silicon ratio is about 0.15. And this ratio is actually 0.34 for Mars. If we assume the Martian mantle has the same chemical composition as what has been proposed by Dribes and Wenke, in their model, I call it the DW model, which is derived from the SNC meteorites, so Shirkatite, Nacknite, and the Chessonite meteorites, based on a bulk CI carbonaceous chondrite composition. Berta and Fay has run some high PT phase equilibrium experiments on DW composition of the Martian mantle, and they found that the iron number of olivine in their run product is about 21 to 25. Think about the Earth. A typical iron number for Earth's mantle minerals is roughly about 10-ish, right? It's like, think about the olivine, the mantle olivine. It's about the phthalite 10 versus like a forsterite 90 or something like that. So iron makes minerals denser. So the enrichment of iron in the Martian mantle makes its density higher than the Earth. What about the crust? Again, based on Martian meteorite studies, people believe that the Martian crust is primarily made of Shirkatite basalts. The Martian Shirkatite is very well known for its low aluminum content. For example, the near primitive Shirkatite Yamato 980459 has aluminum to silicon ratio of 0.12. The more evolved Martian meteorite Shirkatite has aluminum to silicon ratio of 0.16. Compared with the Earth, Morb has the aluminum silicon ratio of 0.4, significantly higher than the Martian sugardite. Think of eclogite, again, which is primarily made of garnet plus amphasite. It is denser than the other mafic and ultramafic rocks because the high density of garnet. The more aluminum you have, the more garnet you have. So in principle, when morb and the Martian sugardite both transform into eclogite at depths, the Martian eclogite will contain less garnet and is less dense than the eclogite transformed from morb in the earth. So let's run through this idea again, okay? Due to the high iron content in the Mars, the ambient Martian mantle is denser than the Earth's mantle. And due to the low aluminum content in the Martian crust, the eclogitic Martian crust has less garnet, therefore is less dense than the eclogite formed from morb after they subducted into the mantle. The dense eclogite formed from morb on the Earth is one of the major driving forces for subduction in the Earth because it is denser than the surrounding mantle. Right now, because Martian eclogite is not as dense as the Earth's eclogite, it is possible that this buoyancy relationship is not valid anymore. As a result, maybe instead of being a driving force, this eclogite versus ambient mantle, this kind of buoyancy thing, can become a resisting force for subduction. In order to verify this hypothesis, we conducted high PT phase equilibrium experiments on Yamato 980459 up to about 16 GPa in 1900 K, corresponding to about 3,000 kilometers deep in the Martian interior. We utilized the 2010 multi-angle press at the high pressure petrology lab at University of New Mexico, and then analyzed the raw product using microprobe. In addition to that, we also conducted a purple X phase equilibrium calculations along the Martian mantle aerotherm. In addition to Yamato 980459, we also calculate the phase diagram for ambient Martian mantle composition, DW model, as well as a more evolved chemical composition, which is similar to the composition of the meteorite sugar tea. So 48 cell assembly are used to run the experiment from 1 to 10 gigapascal, and we use the 10.5 assembly to run the experiment from 10 to 16 GPa. Here are the experimental results on the Yamato 980459. The mineral proportions are obtained from both mass balance calculation and the image analysis. They are consistent with each other. The garnet content remains low at about 20 volume% to about 8 to 9 GPa, which is about 700 kilometers deep inside the Mars. After that, the garnet content increased significantly, again, due to the dissolution of the pyroxenes into the garnet structure. We can see this trend from the microprobe elemental maps as you see on the right-hand side. For comparison, the garnet content in a morb is about 40 volume% at 250 kilometers, and that value is only 20% for Mars at the same depth. It's worth to compare our experimental result with the purple X calculation result. Again, we're looking at Yamato 980459. The top figure shows the calculation result, and the bottom figure shows the experimental result, which is the same one you see in the previous slide. We can see that the purple X suggests the similar garnet content as what we found in the experiments, and the total pyroxene content is also similar. However, at the same time, we can also see the difference. The largest difference is the stability field of orthopyroxene, OPX. Purple X suggested a much larger stability field for OPX than what we found experimentally. Purple X estimated the phase proportions through these Gibbs-free energy minimization. However, for magnesium-rich pyroxene, the Gibbs-free energy of orthorhombic structure is very similar to the monoclinic structure. Therefore, the precise determination of the relative proportions between OPX and CPX is relatively challenging. Fortunately, the density difference between OPX and CPX is small because they are both pyroxenes. So the difference in terms of the OPX stability field does not affect our density estimation of the Martian eclogite, as long as the total pyroxene content is relatively robust. The other difference is the stability field of garnet versus plagioclase. It is well known that the plagioclase to garnet transition takes place at the pressures between 2 to 3 gigapascal. Therefore, we believe that the experimental result is slightly more reliable. You don't see the plagioclase stability field in the Popo X calculation result. The other difference is the stability field of wadzleyite and ringwoodite. You can see from Popo X computations that there is a very small stability field for wadzleyite and ringwoodite at pressures higher than 12 GPa, which we do not see it under experiments. That's probably caused by the unknown or unconstrained thermoelastic properties of the pseudo-iron and member of olivine polymorphs, as well as garnet and pyroxenes. The more evolved marsh eclogite with sugarty chemical composition shows similar computational results. So from now on, our discussion will be based on the experimental result of Yamato 980459. We also conducted like Popo X calculations on bauxilicate marsh and then compare with the earlier pioneering experimental work conducted by Berkta and Fay. Again, you can see larger OPX stability field coming in the Popo X calculation result. This is consistent with what we found, like from Martian eclogite with Yamato composition, convinced us the robustness of our experimental result. And also we see they're slightly different, slightly more Wadsley and the ringwoodite, bigger Wadsley and ringwoodite stability field, comparing the experiment, comparing the Popo X result with the experiments. Anyway, right now we know the mineral phase proportions, and then we can calculate the density profiles for the ambient Martian mantle and Martian eclogite inside the Mars using the thermoelastic properties of these individual minerals. We also, here is what we got for the density. So the vertical axis shows the density difference between the slab crust and mantle for the Earth and the Mars. The black dashed dot lines represent the density difference for the Earth, whereas the orange lines represent the case for the Mars. We can see that because Martian eclogite has significantly less garnet than the Earth's eclogite, the density crossover between the eclogite and ambient mantle would not happen until 300 kilometer depths in the Martian interior, comparing with only 65 kilometers in the Earth interior. Moreover, Martian eclogite need to subduct down to over 1,000 kilometers in depth to reach the level of similar density contrast as what we have for the Earth interior. Remember, the density contrast we show in this figure here is only comparing the density of a small mass unit in the ambient mantle and the slab crust at the same depth. Basically, if you imagine there is a slab subducting down into the Martian interior, at shallower depths, this little mass unit in the slab, right now, it is less dense than the ambient mantle, so this one is likely to float up. But at greater depths, another small mass unit over here becomes denser, so it likes to sink down. However, if we consider a mechanically coherent slab, and we want to know whether this big slab would like to sink or float as a whole, then we need to know the net sinking or floating force by integrating all the small sinking or floating forces from these small mass units altogether. So given several assumptions about the slab subduction geometry, viscosity, and thickness of the slab, we can now quantitatively calculate the net sinking torque of the big slab as a function of slab temperature and subduction length. If the net sinking torque is positive, then that means the slab is dense enough to sink. And of course, the negative sinking torque then suggests the slab would like to float up. Assuming no temperature difference between the slab and ambient mantle, the torque remains negative with the slab length less than 670 kilometers. Therefore, therefore, slabs of this length or less is unlikely to subduct into the mantle. If we consider an extreme case when the slab is colder by about 800 degrees than the surrounding mantle, the slab still needs to be somehow subducted into the Mars by more than 300 kilometers for itself to sink even further. This critical slab length, as you can imagine, is going to be bigger It's going to be higher for colder. It's going to be higher for colder slabs and for warm slabs, and going to be shorter for colder slabs. But in any case, the buoyancy-driven continuous subduction cannot be sustained unless the presumably already existing Martian slabs were somehow already forced into the Martian mantle to the depths of at least a few hundred kilometers. Based on the sinking torque we obtained, we can also further calculate the subduction velocities. You can see that the equilibrium length or the critical length remains the same in terms of subduction velocity. Similar to sinking torque, positive subduction velocity indicates the slab tends to sink, whereas negative velocity indicates the slab tends to float. In addition to that, the subduction velocity we obtained is also very, very small. The fastest speed we can see here is only 0.4 centimeters a year. So that is even slower than the lowest subduction speed or the mid-ocean ridge spreading speed, as you see in this picture over here. Of course, the subduction speed can be affected by many other factors. Changing the assumption would affect our result. For example, shallower subduction angle with higher viscosity would make the subduction more difficult. Changing the absolute thickness of the crust would not affect the critical length, but it would affect the absolute velocities of the sinking, the absolute subduction velocities, as well as the absolute values of the sinking torque. Okay, great. Are we good now? Well. There are two more questions we need to think about. Firstly, is Yamato 980459 the representative chemical composition of the basaltic slab crust on Mars? The second question, are the slabs on Mars just made of basalt? The first question was actually raised by the reviewers. We agree that it is worth to take a look at other potential chemical compositions of the Martian crust. The reviewers have suggested two other chemical compositions for us to look at. One is GUSEV basalt, which is a chemical composition obtained from rover remote sensing data, and NWA 8159, which is among the oldest basaltic meteorite on Mars. Both of them are more enriched in iron and aluminum compared with Yamato 980459, even though still fairly depleted in aluminum compared with the morb on the Earth. As you can see from the list of experiments here, we conducted a few more experiments on these two compositions. What we have found is that a bunch of these dendritic crystals or glass in the run product, which suggested that these run products are quenched from liquids. Since these two compositions undergo partial melting or complete melting at pressure temperature conditions inside the Mars, that means like they are pretty much geochemically very evolved. Considering the limited magmatic differentiation and fraction crystallization history on Mars, these are unlikely to be representative compositions of the Martian crust. So for the first question, even though we cannot say Yamato is absolutely 100% the best composition that we can pick to represent the Martian crust, what we can say for now is at least the GUSEV and NWA 8159 are not or seems not representative from our perspective. So now let's move on to the second question. So are the slabs on Mars made of just basalt? For the Earth, the slabs are made of at least two petrological layers, the top basaltic layer and the bottom lithospheric mantle, as what you see over here. So what about Mars? If we think about it from a planetary evolution perspective, we can consider three different kind of slab structures that are correlated to different evolution stages in the Martian history. When Mars is still fairly young, in the pre-Noachian or Noachian time period, the Martian lithosphere is probably very thin, made of mostly basaltic crust. As the Mars gradually cools down, the lithosphere thickness gradually increases to about 110 kilometers during the Hesperian and most of the Amazonian period. In this time, we assume the Earth-like composite slab with 50-kilometer thick crust and 60-kilometer thick thermolithospheric mantle with the same chemical composition as the ambient mantle. For present-day Mars, InSight data suggested that the lithosphere right now in Mars is actually pretty thick, about 500 kilometers thick. So in this case, we tested a 500 thick slab made of 50 kilometer thick basaltic crust plus 450 kilometer mantle lithosphere. The result for the pure crustal slab case that I've shown you already in the previous slides. So let's look at what has changed for the other two composite slab models. In this slide, you can see that the left figure shows the result for the 110 kilometer thick composite slab, and the right figure is for the 500 kilometer thick slab. You can clearly see that for the 110 kilometer thick composite slab, the critical length that the slab needs to be enforced into the mantle to enable self-sustained subduction decreases from 650 kilometers at 0 Kelvin, like temperature anomaly, to 300 kilometer depths if we assume the slab is about 200 degrees colder. And that value further reduced to 150 kilometers if the slab is 400 Kelvin colder. So the colder composite slabs make slab subduction easier. Even though still not that super easy, you still need about 150 kilometers with a 400 Kelvin thermal anomaly. On the other hand, when the composite slab is 500 kilometers thick, you can see that the critical length quickly decrease from like 600 kilometers to 0 as soon as you assume a small negative thermal anomaly. In other words, subduction is going to be very easy from a pure buoyancy perspective, as long as you do have a 500 kilometer thick slab. So again, from a planetary evolution perspective, when Mars is still very young, the thin Martian lithosphere, primarily made of basaltic crust plus a little bit of lithospheric mantle, is probably easier to fracture and form a multi-plate network near the surface. But at this stage, the buoyant Martian eclogite hinders the subduction. But when Mars gradually cools down, the slab gets thicker and thicker. The potential slab, once formed, would be slightly easier to subduct. However, fracturing a 500 kilometer thick lithosphere and forming plates on the present-day Mars is extremely difficult, if not impossible. Of course, we cannot rule out the possibility that at some point, in the Martian history, the Martian lithosphere cannot, can be not too thick, to form plates, or too thin, like to enable the, self-sustained subduction on Mars. But what we know is that in any case, due to the buoyant eclogite, subduction on Mars will still be more difficult to develop on Mars compared with the Earth. There are also some interesting implications for the buoyant Martian eclogite. Firstly, it can help explain the stability of some very high volcano edifices on Mars. For example, Olympus Mons, with a diameter of 600 kilometers and a height of 21 kilometers, is the tallest mountain on the planet, on any sort of like planets in the solar system. It remains to be a mystery that how would it remain stable, over a long geological history on Mars. In this case, if the crustal roots of Olympus Mons are made of this aluminum poor Martian sugarite, then the denomination of such buoyant crustal roots would be really, really difficult if the basalt to eclogite transition occurs. The overly thickened crust under these very high volcanoes could stay stable over a very, very long time. Also, due to the fact that both delamination and subduction are difficult to happen on Mars, little Martian crustal materials can be recycled back to the mantle. The crust and the dip mantle are likely to separate into two different geochemical reservoirs and would evolve separately through geological time. In addition to that, again, because of not much of the cold materials on the Martian surface can be recycled back to the Martian interior, the transfer of the heat from the Martian core of the mantle and then finally to the surface of Mars is suppressed. So insufficient heat transfer at the core mantle boundary and inside the Mars can result in the demise of the Martian dynamo. as a sort of a byproduct of this work, we also calculated the seismic velocity models of different Martian mantle candidate rocks and compared with the geophysical models derived from the InSight mission, which are shown in the shaded regions in this figure. You can see that the very big uncertainties are shown in these geophysical models. The current geophysical models basically would not allow us to tell whether a Martian mantle is made of basalt or DW composition, oxidized or reduced. But hopefully with more data and better analysis tools, the geophysicists can improve their models in the future that can help us to constrain the chemistry of the Martian interior better. Now here's the summary slide, shows the difference between the Earth, early Mars, and present-day Mars. Basically, due to the depleted aluminum content in the Martian shergotite, the eclogite transformed from Martian crust is unlikely to be dense enough to help the buoyancy-driven continuous subduction on Mars. And of course, to make this a more convincing story, future experiments on wider compositional range are needed. For example, it would be nice if you can conduct some experiments on the with the chemical composition like similar to the meteorite like Black Beauty. So anyway, correct chemistry is important for a planet to be alive. Just like showing this cartoon, like the Earth talk to the Mars like, you have no knife. Well, that's probably because the Mars has a wrong chemistry composition. So thank you all, and I'm happy to take any questions.
All right, thank you, Jen.
Okay.
It's a great talk.
Mm-hmm.
And if anyone has any questions, you can raise your hand or you can put your comment in the chat and I will ask it there. We have lots of clapping from the audience. Carl, you can go ahead and Carl, you can go ahead and unmute yourself.
Oh, hey, Jen. How's it going?
Hey.
Can you hear me?
Yes, I can.
Good. I'm happy to see everything's going so well for you at A&M.
That's a lot of work.
Well, you can always come back. No. Anyway, great talk. I really enjoyed it. And also, Kara, I'm really happy that Forrest is making such a great start with these talks. It's excellent. And it makes up somewhat for the loss of compress. But anyway, looking forward to January. My question has to do with the bulk composition. I think I've pestered you about this before. And you did touch on it a bit. But I think that if you do look at, and yet again, another one of the compositions, as I think I've mentioned to you before, is the bulk composition of Black Beauty. Again, it is it's a breccia, but if you plot the average value of it on the silica versus alkali plot for volcanic rocks, it plots right on top of what is thought to be the bulk composition of the Martian surface based on rover and orbiter data. And so I tend to feel like the Martian meteorites in general, the shergotites, I personally don't think they're representative of the Martian crust. And again, this is a long question and more of a statement, but in order to get something like shergoti, these aluminum depleted shergotites, they are non-chondritic. So somehow they have to be coming out of a mantle somehow that has held back aluminum. And there are some ideas about garnet fractionation.
Garnet fraction, yes.
But
that can help to hold
a lot
some
of that.
aluminum.
You screw up the rare earth element patterns.
Mm-hmm.
So again, I tend to believe that the shergotites are maybe more of a regional phenomenon than global, but that's my take on it. Any response?
I absolutely agree with you on some aspects. For example, the definitely shergotite is not, it's far from being satisfying as a perfect candidate to represent the overall crustal composition of the Mars. Because you can always argue about like the sampling of the shergotite might not be representative enough. It's only from part of it, some regions of it. And I agree that the rover data as well as the the remote sensing data provide a really good complementary, information, for us to know more about what are the potential composition ranges. So one disadvantage of using that's why Black Beauty is so important, because sort of like if we are talking about the remote sensing data, where the sampling is restricted to the very, very shallower part of the Mars. It's like if you're doing a remote sensing on the Earth, what we are going to see are all the soils and stuff like that, and the trees, and so basically from that perspective, the rover data is also sort of more or less biased toward the very, very shallow part, maybe the top 1 meter or 20 centimeter, 1 inch, 2 inch of materials on the Mars. So that's why I think the Black Beauty actually provide a very good information to tell us, at least as a sort of meteorite, you need to have some really violent event to happen on Mars to eject that meteorite to make it arrive on the Earth. So that I think it provide another window to tell us actually some of these compositions that are observed for even the very top, let's say 1 inch of soil, whatever on the Mars, actually, probably, can be a little bit deeper than that. Basically, this composition is not just the very, very top 1 inch, chemical composition of the Mars, can be a little bit deeper, because the Black Beauty actually shows a chemical composition that deviate from the most of the other meteorites that people see, the aluminum depleted, the sugartite. So anyway, my response to it is sort of based on the current assumption that if we believe the meteorites represent a more or less average sampling of the Martian surface crustal regions, not restricted to the very, very thin skin, that 1 inch soil layer of the Mars, then we would say that's what we found.
Yeah,
but with more data coming up,
yeah.
then we should, and I think we should explore much wider composition range as what we see.
I think that's absolutely valid what you're saying, because especially with respect to remote sensing. I mean, the other pitfall, of course, in all of these assumptions is that Mars has a fairly homogeneous mantle, right? And if you look at the Tharsis bulge, I mean, I wonder if that's the same all the way down versus places that are not under Tharsis,
Yeah,
so
that's right.
The Earth may be more homogeneous than Mars in terms of that. But anyway.
Probably, yeah.
That's another one. That's another one.
That's another one, absolutely.
Anyway, good job.
Thanks, Carl.
All right, Elvira, you could go ahead and unmute yourself.
Thank you. Can you guys hear me?
Yes.
Awesome. Thanks. Jin, thank you for a great talk. Very interesting. I learned a lot. I have a question because I'm biased probably. I mostly think about subduction on Earth. And then, typically, I like how you describe the trade-off between you need the negative density, so negative buoyancy for it to subduct, and then you need to be able to overcome the strength of the slab. When we think about that on Earth, my question about the contribution of this transition to eclogite. When we think about it on Earth, the thermal anomaly and the size of the slab are so large that the crustal component that is just a few kilometers thick, I figure you can scrape the entire crust off and it'll probably still subduct. On Mars, correct me if that's not true. And also, are you making kind of the point that on Mars, this eclogitic component is more important, perhaps because it is thicker? Is it making a bigger contribution to the overall negative buoyancy?
So the problem, right now for the Mars, is we don't really have a very good understanding about what the lithospheric structure is, basically. So even though for the InSight data, which is suggesting a 500-kilometer thick lithosphere, right now, that's back in the 2020, the year before last year, so 2020 or 19-ish sort of study. And then the most recent study, just published, I think last month or earlier this month, is showing that actually if you're assuming a partially molten layer near the core mantle boundary of Mars, then the lithosphere can be significantly thinner. So it's really, really controversial, let's say, for the for the Mars, like right now. And we adopted this model based on the previous paper, which suggests the different kind of basically how the lithosphere grow like as a function of time. But this can change at any point with new models and new results coming up. And then for the Earth case, if you only so I agree with you. Like if you're thinking about the size of the thickness of the basalt, it's only about 10 kilometers. I don't know, less than 10 kilometers. The slab itself, the entire thickness is about 100 kilometers. It may not seem to be that important at the beginning, but there's always one thing which is very important. That is like how do you even initiate the subduction of the slab, and how do you in the initial phase, and then how do you provide enough force to actually drag it downward. So from that perspective, I don't think the surface, the very top layer as a very dense layer, the role is that small from that perspective. So when you just start it, you need to have a relatively dense thing to actually push it downward, help it go even further. That's my sort of take on the role of the basaltic crust over here. And then the other thing is the density contrast between basalt versus the other part of the slab. Sorry, not the other part, the ambient mantle is very, very big. You can do a transformation, transferring the thermal anomaly into the density contrast. And to compare with eclogite, it's actually like 5 to 10%. That's huge. Even though you're looking at the fraction, the volume is not that much, but the intrinsic density contrast is so big that it is it's indeed just very important. Hopefully I answered your question.
Yeah, I hear you. I think it's very interesting. Thank you. I think it'd be useful to put some numbers on it, just in terms of volume. When you calculate the negative buoyancy, the 100 kilometers negatively buoyant cold slab for Earth and mantle. And I'm just curious. I have very little intuition for what the Martian, with the different phase transition would actually look like. But
it would
yeah,
be nice
perhaps
to
I
do
understand.
it would be nice to do just a quick calculation. It doesn't cost that much time, right?
Yeah,
so
for sure. Thank you.
In the chat, Anton asks, if you could propose an instrument or entire mission to be flown to or above Mars, what would you want most? Are there certain ground or below ground data that would be most valuable to your research?
Wow, this is like I don't know, it's like $1 billion project. You're making me thinking too much.
You have imaginary money, so you can come up with anything you want.
Oh God. I think there are two things that I want. One is already actually people have been doing like right now is the direct sampling, of Mars. So we have Mars sample return, mission right now, which is ongoing. I'm probably not going to be able to actually dig the samples and then do the chemical analysis of them, but I'm curious about what comes out from that. This is like the first direct sample we get from Mars. This is not Martian meteorite. This is a direct sample. I think that's very valuable from that perspective. And if we can do a drill, like like drill through a big hole through Mars, that would be even better. But I think that would be even more difficult. The other thing which I think is very valuable is because right now we only have one seismometer on Mars. So that really restricted the resolution as well as the amount of knowledge that we can basically there's just limited things we can do with only one seismometer on Mars. So in addition to that, because it turned out to be that the Mars core is a lot bigger than people originally thought. So the shadow zone is going to be a lot bigger. So that means the sampling region that we're able to sample like through the Mars is going to be even more restricted. So having more than one seismometer, hopefully 3 or 4 or 5 seismometers on Mars will help us to constrain the structures significantly better. So we can have more of a better saying about what rocks is basically making the Mars. That is very important. Like if you look at the current data, you can't even tell the difference between a supposed to be like, where is it? We can't even, we can't even tell the difference between the ambient mantle versus the basalt. I mean, it's just changing too much. If you see over here, the range is just too much. So if we can have a much better understand, like seismic, data from the Mars, constrain the Martian interior structures much better, then we can have a much better saying about the chemistry of the Mars as well. I think those are the things I'm thinking about. direct sampling of the Mars. So which is a simple return. Hopefully we can drill through the Mars like 1 kilometer deep. And then and then the other one would be sending like a 3 or 4 or 5 seismometers onto the Mars. We'll walk on the Mars. That's great.
Anton says thank you for the detailed answer
Mhm.
and the excellent talk. We will thank Dr. Zhang for her great talk. Love to see something about Mars. It's really fun. And thank you
Okay,
everybody
great.
for joining us today.
Yes. Thank you very much. And thanks. Goodbye, everyone.